Now we'll see ways to get a bunch more functions that a power series converges to. First off, so we know one so far, that the summation of x to the n equals 1 over 1 minus x, or x over 1 minus x, depending on whether it starts at 1 or 0. Now here's some ways to get a bunch more functions that power series converge to. First of all, if a function f of x converges, then the power series converges to that function f of x. Then so do f prime of x and antiderivative of f of x, the derivative and the antiderivative. In other words, the antiderivative and the derivative both have a power series that converge to them. That's going to be two ways to find new convergent power series that converge to a function. Take one that you know and take its derivative or its antiderivative. And the other two tricks are to substitute in for x, and what you do is you take a known power series that converges to something and you substitute on both sides of the equals, or multiply by a factor, and those you have to usually multiply by a polynomial factor, usually x to a power, maybe a constant as well. So for instance, we'll do some examples. I'm going to use 1 over 1 minus x equal to summation n equals 0 to infinity x to the n. And I'm going to do examples where the question says, find a power series that converges to blank. So for number 1, I want to find a power series that converges to 1 over 1 plus x. So it's a puzzle solving exercise. What you have to do is figure out how you can make that look like the pattern of the known example above, 1 over 1 minus x. So if I have 1 plus x in the denominator, I could make that 1 minus negative x in the denominator. Same thing, just a little algebra. Now it looks like 1 over 1 minus. And in the above, 1 over 1 minus x is equal to summation x to the n. So I could take that negative x, and I see it as being substituted in for x. So I substituted in for x in the big sum as well. I have negative x to the n. So now I know that 1 over 1 plus x equals the summation n equals 0 to infinity negative x all to the n. I can go further for the second example. Now I want 1 over 1 plus x squared. So actually I could look just at the previous example. Or I could make that 1 over 1 minus negative x squared. Either way, what it turns out is that it means I'm substituting in x squared, or negative x squared for x in the original, or x squared into the example in number 1. So that means it's the summation n equals 0 to infinity negative x squared to the n. That's what 1 over 1 plus x squared is equal to. And you can simplify that a little bit too. That's a little hard to read, but it's n equals 0 to infinity, negative 1 to the n, I just distributing the exponent n, and x to the 2n, distributed it onto both powers. Number 3 then is x cubed over 1 minus x. So this one is has a 1 minus x in the denominator already, so I can just think of it as x cubed times 1 over 1 minus x. So that means I can just substitute in the entire sum for 1 over 1 minus x, but I just multiply it by x cubed. So it's equal to x cubed times the summation n equals 0 to infinity x to the n. And then you can pull in that x cubed. It doesn't have any n in it, so it's a common factor of all the terms of n. And when I pull it in, I can add the exponents, x to the n plus 3. Here's a couple with the derivative and, both of these are antiderivatives, I guess. So that's okay. We'll do some derivative ones very soon. For the antiderivative ones, a natural log of 1 plus x. That is the antiderivative of 1 over 1 plus x. Now 1 over 1 plus x is the example I found up here in number 1. It's the summation of negative x to the n. So I could also write that as negative 1 to the n and x to the n, and here I have raised and divided, so x to the n over n. Now that does start at n equals 1 to infinity, so that means you have to do show a little bit more work there to get from number 1 to number 4. I'll probably do that one on the board. You can work out some of the steps, but it might be good to show more work. It's correct the way it is, but it's because I have n equals 1 to infinity starting underneath it there. Here's one that's a little bit of fun for the finish. The inverse tangent of x is the antiderivative of 1 over 1 plus x squared. Now we have 1 over 1 plus x squared up there. It was negative 1 to the n, x to the 2n inside the summation. So here's the deal. You can take the antiderivative inside of all the pieces. And this one I didn't skip any steps. So I just keep that constant, negative 1 to the n. Then I raise and divide. So it becomes x to the 2n plus 1, raised it, and divide by that same number, 2n plus 1. So there's the infinite series that converges to the inverse tangent of x. And then you can do numbers. What does the summation n equals 0 to infinity, negative 1 to the n, over 2n plus 1 equal? What does it converge to? Well, it looks like the same thing as inverse tangent in the previous example, but it just has a negative 1 to the n, no x to the 2n plus 1 on top. Well, I notice that's actually 1 to the 2n plus 1 on top, because 1 to anything is 1. And now when I write it like that, I see that it's exactly the same thing as if I put a 1 in for x. And that means I must have been able to put a 1 in for x in the inverse tangent. And the inverse tangent of 1 is pi over 4.